Hi, this is the video on the Gibbs free energy. So we're not quite there yet. We're almost there. There it is. There's the video on Gibbs free energy. So this video will be a little short. The slides leave kind of a little bit to be desired. But basically what we're going to do is we're going to go through some of this stuff. And if you have any questions, you can see myself or you can see Mr. Walsh, whoever your teacher is. Also, we can spend a little bit more time going a little bit deeper into some of these things. So, for example, I present you with this equation here that says the change in the entropy of the universe is equal to the change in entropy of a system plus the change in the entropy of the surroundings. If this value is greater than zero, in other words, when a system undergoes a change, if the change in the entropy of the system plus the change in the entropy of the surrounding that results from the change in the system, if that increases the entropy of the universe, we find that the process is spontaneous. If the process causes a change in itself, in its entropy, and it also causes a change in the entropy of the surroundings, if the two add together and they come out to be equal to zero, that means the universe's entropy has not changed and the process is in equilibrium. So if a process is in equilibrium, the universe's entropy will not change. If a process is spontaneous, a change in the system which causes a change in its entropy will also cause a change in the entropy of the surroundings. And when you add those two together, it's greater than zero. We know that the process is spontaneous. Now, it is rather difficult to, on a daily basis or regular basis, to measure the entropy of the universe in order to determine whether or not a process is spontaneous. So a guy by the name of Gibbs, who was at this little school, it's a little school in Connecticut. It's in New Haven. What is the name of it? I think it starts with a Y. Yale, that's it. Gibbs was down at Yale when he came up with something known as the Gibbs free energy. For a constant temperature and a constant pressure process, delta G, which is known as the change in the Gibbs free energy, is equal to the delta H of the system minus T delta S of the system. I can go into that a little bit more deeply with you as to how a simple way, that is, a simple way in which we can come up with this particular equation. And again, this is called the Gibbs free energy, where delta G is the change in the Gibbs free energy. If delta G, the change in the Gibbs free energy of a reaction, is less than zero, in other words, if the value is negative, the reaction will be spontaneous in the forward direction. If delta G is greater than zero, so the change in the Gibbs free energy is positive, the reaction is spontaneous in the in the reverse direction, but is non-spontaneous as it is written in the forward direction. And of course, if delta G is equal to zero, then the reaction is equilibrium. Again, if you talk to me, I'll be happy to give you a little more details as to how this equation came about and what it means. But the basic idea of what this means is this. After you consider the delta H, that change that occurs, right? The change in the enthalpy, that occurs when a system undergoes a change. And if you consider the entropy change in which a system, that happens to a system as it, again, undergoes a change. If you consider both of those things, which both of those are energy phenomena, delta H is heat, right? And delta S deals with entropy, although T delta S ends up being also an energy phenomena. If there's any energy left over to do work, then you have a delta G, which comes out to be negative, and the process is spontaneous. If there is no energy left over to do work and you have to do work, then the process will not be spontaneous. But if it turns out that delta G comes out to be equal to zero and no work needs to be done, nor is any work being given off, or there's no energy to do any work, then the process is in equilibrium. Like enthalpy, we can define a standard free energy of reaction in terms of delta G. It is the free energy change for a reaction that occurs under the standard conditions. For a reaction of A with a coefficient of A and B with a coefficient of B, reacting form C with a coefficient of C and D with a coefficient of D, delta G of the reaction under the standard state conditions of the little circle or knot next to the G stands for is equal to C delta G of formation of C plus D times the delta G of formation of D minus A times the delta G of formation of A plus B times the delta G of formation of B. So it ends up being the delta G of formation of products minus the delta G of formation of reactants, as we said in this statement above and the statement below it. The standard free energy of formation is the free energy change that occurs when 1 mole of a compound is formed from its elements in their standard states, which is basically very similar to the delta H of formation in terms of its definition. Delta G of formation of any element is stable in its stable form, is equal to 0, just like delta H is equal to 0 for any element in its most stable form. So the standard conditions for gases is 1 atmosphere of pressure. For liquids has to be a pure liquid. For solids has to be a pure solid. For elements, delta G naught of formation is equal to 0. And of course, if it's a solution, it has to be 1 molar concentration. So those are the standard states. Those are important that you remember those standard states. Those standard states are important because you'll be using them in a variety of different ways in different things throughout the rest of this course. So what is the standard free energy change for the following reaction at 25 degrees Celsius? Remember, standard state is 1 atmosphere of pressure for gases and that the liquids involved be pure. There is no statement as to what the temperature is. So delta G naught of the reaction is equal to sum of the delta G of formations of the products minus the sum of the delta G of formations of the reactants. If you check the appendix in the back of your book, you can find the delta G of formation of a variety of different things, as well as the delta H of formation and the entropy of specific substances. Delta G of the reaction is going to be equal to 12 times the delta G of formation of carbon dioxide, plus 6 times the delta G of formation of the water, minus 2 times the delta G of formation of C6H6. And again, be careful, make sure that you are picking water as a liquid, not gaseous water. And so please make sure that you are cognizant of what state of matter that the substance is when you go into the textbook and find those values of the delta G of formation. And of course, you can see oxygen is not included. The O2 is in oxygen in its most stable state. And so delta G naught of the reaction comes out to be a negative 6,405 kilojoules per mole. Is the reaction spontaneous? Well, I don't like this particular question because we're finding the delta G under the standard state conditions. Delta G under the standard state conditions does not really tell us about the spontaneity of a reaction. What it does is it tells us whether or not the reaction is favored in the forward reaction or whether or not it favors the reverse reaction. So that's what the delta G naught tells us. If our delta G naught is negative, it favors the forward reaction. If our delta G naught is positive, then it favors the reverse reaction. And if our delta G naught is 0, we are in an equilibrium situation. And depending upon the temperature, it can go one way or the other. It can either begin to favor the forward reaction, depending upon the temperature. I'm not going to go any further into that, but you'll see later on. So again, I don't like to use the term spontaneous. I prefer to think about this in terms of whether or not the reaction favors the forward or the reverse. So if we are looking at delta G, and we are considering delta G when we are not discussing the standard state conditions, here is a chart that helps us to understand what is going on in terms of temperature as to whether or not a process will be spontaneous. So when our delta H is positive and our delta S is also positive, a reaction will proceed spontaneously at very high temperatures. At low temperatures, the reaction is spontaneous in the reverse direction. So the problem is that our T has to be very large in order to subtract it from the delta H, since both our S here, our delta S, and our delta H, since they are both positive, T is going to have to be a large number so that T delta S is greater than delta H, and when we subtract it, we will get a delta G that is negative. When delta H is positive and delta S is negative, delta G is always going to be positive. Therefore, the forward reaction is not spontaneous, but the reverse reaction will be spontaneous under all temperature situations. When delta H is negative and delta S is positive, delta G will always be negative because this is a negative value, this is a positive value. A negative value minus minus a positive value is always going to give us a negative value. So delta G is always going to be negative. It's going to proceed spontaneously in the forward direction at all temperatures. And last but not least, if delta H is negative and delta S is negative, the value of T has to be small at low temperatures. Then when we subtract this from this, when we subtract T delta S from delta H, if T is small, we will end up with a delta G that is negative. Temperature and spontaneity of chemical reactions continued. This is the decomposition of calcium carbonate to form calcium oxide and calcium dioxide, or carbon dioxide, excuse me. The delta H under the standard state conditions of this process is 177.8 kilojoules per mole. Remember, we're talking about a pressure of 1 atmosphere for the carbon dioxide. Both the calcium carbonate and the calcium oxide have to be pure. The delta S of this process under the standard state conditions is 160.5 joules per Kelvin mole. The delta G naught is under the, right? So it's delta G under the standard state condition is equal to delta H naught minus T delta S. At 25 degrees Celsius, the delta G naught is 130 kilojoules per mole. That is telling me that it is favoring the reverse reaction. Well, at 835 degrees Celsius, it turns out that their delta G naught is equal to 0. We can tell you a little bit more about how we came up with this value of 835 degrees Celsius. If you come on up and we'll have a conversation about this, and I'm sure Mr. Walsh will do the same. We can give you a little information as to why, but one of the more important things that we need to discuss here is this particular graph. We see, and we can see by this graph as to why it's the delta G naught is telling us more about whether or not the process is favoring the forward or the reverse reaction. We see that we don't reach the standard state condition until we reach a temperature of about 835 degrees Celsius. That's where the 835 comes in. The 835 degrees Celsius is a temperature at which the pressure of the carbon dioxide is now at 1 atmosphere, and it is now has reached the standard state condition. So we can see that the pressure of carbon dioxide, not much is happening, not much is happening, not much is happening. The pressure of the carbon dioxide is very low. So if the pressure of the carbon dioxide is extremely low, we can see that it's favoring the reverse reaction. There isn't much carbon dioxide present to have a pressure. We see that as we get closer to that temperature, though, the pressure of the carbon dioxide rises. And we can see we are getting to the point where the value of delta G naught becomes equal to 0. In other words, it's in the beginning, it's favoring the the reverse reaction. But now more and more that forward reaction is coming into play. And eventually it is at this temperature of 835 degrees Celsius that delta G becomes equal to 0. And so we have reached a situation in which the reaction is at equilibrium, but the pressure of carbon dioxide is now at 1 atmosphere. If we begin to raise that temperature above 835 degrees Celsius, the pressure goes above 1 atmosphere, which is now telling me that it's beginning to favor the forward reaction. So that's why I say to you, the delta G naught doesn't really tell us about the spontaneity. What it tells us is whether or not it favors the forward or the reverse reaction under those conditions. Last thing we want to talk about is phase transitions. Phase transitions, basically think about phase transitions as taking place in terms of an equilibrium state. When delta G is equal to 0, delta H minus T delta S is also equal to 0. For water transitioning from a liquid to a gas, delta S is equal to delta H over delta T. If we plug in those values, we will get the delta S of the process for which water is going from a liquid to a gas. So here's the rate of evaporation. The rate of condensation has to increase over time because at first we have all evaporation going to a gas, and then as a gas is formed and the reverse reaction is taking place, we see that the rate of that is approaching the rate of evaporation. When the two rates are the same, we have established a dynamic equilibrium, and that's why we set our delta G equal to 0, and therefore we can find the delta S at which the transition is occurring. It turns out it's 109 joules per Kelvin mole.